every year it's sort of, we get past CHIUW, we have a great keynote, and then I'm always like, oh, what are we going to do next year? Who are we going to get? And this year I'm super excited about our keynote speaker, Éric Laurendeau from the École Polytechnique Montreal. And I'm going to call him Eric from now on because my 9th grade French hasn't stuck with me so well. I could give you kind of Eric's kind of by the numbers CV style introduction, but I always find those really boring as an audience member. And you can read about it online. The CHIUW webpage, we've got a little bio. The one thing I will call out is he got his PhD from the University of Washington, and there are a number of us on the Chapel team who are Huskies. So maybe that's part of what we like about him. But what I wanted to do instead was just give a short anecdote about sort of how we got in contact with Eric and his team to begin with. And this goes back a couple of years to January of 2019. And I got some emails like almost completely out of the blue from some students, or well, I should say students and postdocs in his lab. And so I'm just going to read some excerpts from it. The first mail, January 2019. My colleague Simon and I are working in numerical fluid dynamics in the team of Professor Éric Laurendeau. First, we would like to mention that we absolutely love this new language that you and your team have developed. We think that you really succeeded in creating a language that is fun to work with while maintaining performance and efficiency. As a first exploration, we reproduced in Chapel an old 2D CFD code written in Serial C, and we were quite impressed with the performance. And this is the kind of mail, if you're developing a language, you're going to spend a lot of your time trying to defend why you exist and why people should pay attention, and a lot of doubters and naysayers. So this is the kind of mail that, you wish you could get every day. And then a couple of months later, we got a follow-up mail. We're currently in discussion with our research director regarding the next CFD developments for the lab. We will probably, 90% sure, completely rewrite our simulation software. Originally, before we learned about Chapel, this should have been done in C++. Now, Mathieu and I think Chapel would be more suited for our application with regards to efficiency, development speed, and maintenance. However, our director is concerned about the viability of the Chapel language. Do you have any arguments to show him that the language will continue to be actively developed in the future? And this is the kind of mail you also kind of love to get, but you hate to get, because none of us can predict the future. We've invested a lot of time and interest in pushing Chapel forward, and we are optimistic and hopeful that it'll be successful. But of course, you can never promise someone that it'll be around for all time. So I gave kind of a response being as honest and upfront as possible, but encouraging, and sort of waited to see what would happen. And happily, they have ended up using some Chapel. So to me, this is an exciting group of exciting case study of a group who's wrestling with their ability to write good code quickly and have it perform well, versus the tension of working in a technology that's not as adopted as C++ or MPI or things like that. So with that, I'd like to welcome Éric Laurendeau to CHIUW to tell us about computational fluid dynamics in high performance computing in general, and how this C++ versus Chapel debate turned out for his team specifically. So Éric, you want to take it away?
Yeah, thank you very much, Brad. Welcome to everybody to this talk, and I'm happy that Brad gave the right tone. I like being non-formal, and I'm professor, but doesn't mean anything. If you want to know my resume, I really enjoy skiing. So I skied the Pyrenees when I studied in France, and I skied the Rockies. And summertime, I played tennis. So that's as far as my resume goes. So, the aircraft design is, I'm going to give you a crash course, I say, because it's kind of like just a theme in order to share our experiences across different fields, computer science and applied mathematics. So I'm going to first tell you a little bit about what aerodynamic is, and then I'm going to make the link to computer science. So first, I'd like to acknowledge all the sponsors of my laboratory's research. So namely Bombardier, Crane, that is now HPE, and CAE, and then NSERC and CREAC are like the NS Natural Science Foundation, NSF of Canada. And most of you may not know, but Canada high performance computers are all linked together. I guess because we're more of a socialist country, we've pulled up all HP for university. And so if I want to run on supercomputers in British Columbia, from Quebec I can, and the Compute Canada and Compute Quebec are like the branch that make that happen. And I thank all my students, that some of them are here listening. And I took some slides from internet, so I thank internet and the organizing committee. And so here's a crash course. So short of being rocket scientists, we'll do airplane, but basically it's more or less the same. So the aerospace and aeronautical community are the same. And then I'm going to talk about CFD, high performance computing, and then some vision. So, okay, why École Polytechnique, you know, we're not MIT and Stanford, and I know those Ivy League schools, you know, and they're the best in the world. And so why Montreal? So short of Polytechnique, why Montreal? So just for information, we're the third largest aerospace cluster behind Toulouse and Seattle. So Seattle is number 2. I hate to break this to you, but now that you have activities in North Carolina and Chicago, Airbus is number 1, Seattle number 2, and we're number 3. And maybe different is the only region where if you would just to put a curtain around the city, we have all the manufacturing to actually design, build, and fly, and test, and certify an aircraft, which is not the case in the other cities. Also, the United Nations are represented in their civil aviation organization in Montreal at ACAO, that is based in Montreal, and the Air Transport Association. So when you buy an airplane ticket, each airplane ticket is certified by IATA, and it's right here downtown Montreal. And they're the one who set up the global warming goals, the secure flights, and planet-friendly travel, so recycling. All these target goals are made right here in Montreal, and you have representatives from everybody that are here. So notable things in Montreal, so we have some great industries. So Bombardier makes all kind of aircraft now. They used to make many, now it's kind of like Airbus, but one of our civil aircraft for $1. So now it's an Airbus 220. Pratt & Whitney makes several turbofans for business jets. So if any of you have a business jet, chances are you're flying with a Pratt & Whitney Canada engine. Bell Helicopter is the civil branch of Bell in Texas, in Dallas. And so all civil helicopters made by Bell are made and flight test right here in Montreal. CAE owns 50% of the commercial market for flight simulators. So all the Boeing 787 and 737, the CAE flight sims are made here in Montreal, and we have second tiers. Also, well, in terms of metrics, again, I'm not talking about MIT and all those great universities you have in Boston, but in terms of number of students and student ranking and with various metrics, so integrated metrics, we're number 1 by the QS World Ranking Index. It doesn't mean anything, but it means something. So we're ahead of Boston, and we rank number 1 in North America, number 6 in the world. And we also have a world-class AI hub, and it's led by Professor Yoshua Bengio, who won the Turing Award in 2018 with Jeffrey Hinton, who's at Google Lab, and Yann LeCun, who's at Facebook. And even I've heard that Yoshua would be at Apple, I believe, but he always stayed in university. So we're really thankful that we have Yoshua Bengio here. So how we make aircraft? So it's very easy. You just go sequentially. So you study the feasibility, you know, let's say, should we do a supersonic aircraft? And you go and see customers. So customer are involved in this feasibility phase. You know, would you like to fly London, Paris supersonic flow? And you say yes. And then you go into conceptual phase, and then you go back to the client and you say the airplane will cost $100 million. And if they say yes, then you say, okay, let's design the plane. So you design the plane in this third phase, their definition. And then the clients say, well, you know, the performance is there, the cost is there, 100 million. So you've got to go ahead. And then you start planning and developing the aircraft. So now you do flight test aircraft, you certify them, and you deliver them. So that's how it is. And so the key is it's very cheap to study the feasibility phase, and then the cost keeps growing exponentially. And once you're past the go ahead, that means the bank gave you $10 billion to develop the project, and then it's a go. And typically, that's how it goes. Now, in reality, it's not that straightforward. So often after each phase, you study the feasibility and you realize, well, we're not there yet. And you come back. And that was the case for the C series, which is an airplane now called the Airbus 220. That plane in 2005, the business case was not met because we didn't meet the CO2 emission standards. And so we came back to the drawing board, went back again. And then once we had the right engine, we had the go ahead. And in the States, you're right now living I'd say financial catastrophe is Boeing with the 737. You may have heard that there's been 2 aircraft crashes with passengers, unfortunately. And so you would have a real flight certified aircraft that needs to go back to the drawing board. And right now, Boeing added about $15 to $30 billion to their expenses, and not talking about human loss as well. So that's how the reality of aircraft design. So how to treat aerodynamics. So I'm gonna just take a little vision there. So there's electromagnetics for lightning strikes, there's structures, there's engines, and there's fly-by-wire, composite material, but here I'll focus on aerodynamics, that's my area. So drag, if you buy a car, you know that you have some good cars and bad cars in terms of fuel consumption, so drag. But then there are more that are in security, so stall. So that's like when an aircraft takes off at too low speed and it just can't take off. Buffet limits the transonic flight. And we are basically, aerodynamic are key in the development metrics. So after the first wind tunnel test, the drag, which is the consumption of the fuel consumption of the plane, is a key metric for go ahead. And the first flight tests are go ahead for certification. And it's been aerodynamic, the historical source of major catastrophe. So technical, human loss, and financial, like the Boeing loss. So Boeing has hit technical hurdles, human hurdles, and financial hurdles, all because of aerodynamics. So the 737 MAX 8 is due to the aerodynamics they made. They used large engines on a plane that was not made so. And so instead of redesigning everything, they decided to add an augmentation system, MCAS, and that led, one thing leads to another, and that led to a potential security threat. So there was, if a pitot tube was feeding wrong information, then the flight system was making the wrong decision. So what are the methods used for aerodynamic analysis? You have flight testing. So this is the C series of Bombardier that is now an Airbus product. So it's basically $100,000 an hour to do a flight test. Now, getting a flight test aircraft takes $1 billion. So 100,000 is a lot, but you need 1 billion to get to the flight testing phase. That means you have a certified flight test. So that means that already this flight test has an experimental flight test certification stamp from Transport Canada or FAA, and you've spent 1 billion when you're in that phase. Now you may use wind tunnel tests, and they're much less expensive, 1,000 to 10,000 bucks an hour. But to get there, typically you already invested in your company $10 million, if not more. And then you have the Computational Fluid Dynamics CFD phase, which is $100 to $1,000 an hour. And to get the prototype of a full aircraft, it's 1 million. And so right now, all activities in commercial and space flight is towards numerical analysis. That's the way to go. So what is the insertion of CFD is that there used to be wind tunnel tests that would occur after certification, and CFD would be done in the design phase, and then flight testing would ramp up and you would certify, enter into service. And what's happening is with CFD, if you do more and more CFD early in the design process, that's going to happen that your wind tunnel cost will go down and you won't rely on it so much, and you're actually going to reduce flight testing. And so there used to be 20,000 wind tunnel hours, and now we do 4,000 wind tunnel hours. And likewise, we can reduce flight testing a lot. And reducing development schedule is key for performance metric for industry. So you want to lower risk, you want to lower costs. So what is CFD? So CFD involves physics. So you want to model icing, you want to model subsonic flow, supersonic flow, laminar turbulent transition. These are all physical phenomena that you want to model. And then you have applied mathematics. So you take these models and you look at mathematics for the model. So we're talking about nonlinear partial differential equations. So those who are doing applied mathematics, you have maybe heard of elliptic equations, parabolic and hyperbolic. This is key. And then you discretize these equations in a supercomputer. And now you hit about all these problems. How can I solve my problem on a supercomputer? So you can say that aerodynamicists are failed physicists, we're failed applied mathematician, we're failed computer scientists. So aerodynamic is a field where even though you want to predict the aerodynamic performance, and I've been so 15 years I worked at Bombardier, so I was 15 years in industry, and my VPs would say, Eric, you're an aerodynamicist. You're not a physicist. You're not an applied mathematics, and you're not a HPC person. So why do you need all these? And so it's not easy to find the right people, the right training for treating aerodynamics. So you need all these. So yes, the students in my lab are tackling these at various levels, and we need to tackle that as a society, this multidisciplinary problem. So here's an example that limits the maximum flight of aircraft. So if you fly into a transonic regime, what happened is you got hyperbolic region, which is supersonic flow, then you have a shock wave, and the subsonic flow is around, and it's elliptic, and then you have a boundary layer we call, and you have flow separation, and that's parabolic. And so all these phenomena needs to be monitored, and if you tell me you need to do a space shuttle that is supersonic, then it's easy because you only have supersonic flow and you only have hyperbolic. If you tell me do a small UAV that is subsonic, that's easy because it's linear flow. But if you do transonic, then you have all these. So it's like taking a picture of a human being and the mountains in behind and make sure that you capture all the scales. So that's very difficult. So I've shown you the three, the physics, the mathematics, and the high performance computing. So I'm gonna work through the workflow. So there's many steps. So first you need parameterization. So non-uniform rational B-splines, the CAD, you need to put that into the model, and that ultimately will become your design parameters. Then you need closed surface. So if ever your geometry is not closed, then you have gaps. If you have it, we need machine accurate geometry representation. So if you take a CATIA Pro EUG CAD models, if they're 10-6 tolerances, that's not good enough. We need machine accurate 10-16 double-digit precision geometry surface representation. Then we take those geometries, and via partial differential equation, we make nice meshes that satisfy orthogonality constraint and all these. So we can make some very nice discretization around iced geometries. We basically go now to 1 billion unknowns. Then we solve the flow, we solve the droplets, and we're very close in my lab of doing COVID droplet studies. So we study the droplets of cloud particles, but some of these algorithms can be used to study COVID droplets. We're not doing this in my lab, but we have similarities. And then you do post-processing, which is important in terms of multi-physics. So you advance in time the ice shape that accumulates. And yes, we do have flight pilots that test such ice shapes on aircraft. Moreover, we typically have source code. So Boeing, Airbus, all have their own proprietary software. And once you have these proprietary software, you can start doing optimization. So without the analysis, you cannot do the optimization. So I've been working, so I'm old enough, I'm 53. My boss at Bombardier used to work with wooden models in the wind tunnel. And when there was too much acceleration, they would take a file and they would just sand the wooden model in the tunnel. So that was optimization, live optimization. And I've seen people doing bobsleigh and ski optimization in the wind tunnel, and they would take various shapes and you would just see the drag. And they would hold on various skiing and bobsleigh riding position. But now we can do it with numerics. So you have your parameterization and you have your flow solution, and you put that in a optimization. So some of you, you're computer scientists, but some of you may have seen optimization courses where you have gradient based. So you go in a gradient and you try to find yourself in the minimum. You want to minimize drag or fuel consumption. You may want to use genetic algorithms to arrive there. So with genetic algorithms, you need millions of evaluation. That's the difficulty. And so the key for success is devising models that are precise, both in terms of their physics, numerics, and geometry. You need computer resources and algorithm robustness so that when you evaluate 1 million of these, you never get a none or a failed. And you need to devise orthogonal dimensional space in your optimization. The physics of turbulence, so crash course in turbulence. So laminar flow is when you pour olive oil in your salad. Yeah, the flow is very nice, but then you can see that if you have a faucet, it comes with a little droplets that kind of like are turbulent. And so you change into turbulent flow. And then you realize you don't, but Kolmogorov realized that there's an energy cascade from large scale turbulence to smaller scale until the last scale becomes heat. So you can see this if ever you see a large urban fire. Sometimes you see this or a forest fire. You'll see those big scale eddies, small scale eddies, and your eye cannot see it, but there are small eddies that dissipate into heat. And so we can model these. So when we model these, we have DNS, direct numerical simulation, where you don't model anything. And that means that you have to resolve very, very tinily all the scales. And then you have LESDS. So going down, you have simpler models. And on the right, you have other equations that have been studied by mathematicians. Then the physics of turbulence comes into play. You may say, I'm going to study steady flows instead of unsteady flows. So you can make the problem simpler. Then you can have viscosity, non-viscous, low Reynolds number, high Reynolds. So this is like jargon. You don't know. Hopefully you don't understand this right now, but the takeaway is you have physics comes into play. And furthermore, jargon there. And then you can find ways of maybe using asymptotic match, asymptotic expansion to do the coupling between various methods, and you can have speed up so that the industry can speed up their model. So in industry right now, we're not using very detailed turbulence model. We're mostly involved in doing RANs. So to maybe bring perspective and bring vision into all this jargon, NASA, so maybe that's a takeaway for you, is NASA has studied this, and they say that they have a vision for 2030 about computational fluid dynamics. And their vision is that NASA should develop simulation-based analysis and design, so the crash course I gave you, enable rapid CFD technology maturation, and that goes through, interestingly enough, HP systems for large-scale CFD, computational validation campaign instead of experimental validation campaign. So this is important. It basically tells you that right now, we won't do experiment. We will do computational experiment, maybe akin to the mRNA vaccine that are no more vaccines. They're kind of computational vaccines, if you want. and maybe we can do away with experimental testing. And there have been instances where computational validation was used for certification of aircraft. Now, these were a narrow region, but it can be done. A good example of computational validation is the Mars lander. They made this drone fly on Mars. No way you can do experimental of the lower density of Mars. So you have to validate this helicopter that flew on Mars only with computational methods. And finally, NASA sees that we need to develop, foster, and leverage improved collaboration across scientific engineering communities. So what Brad just hinted at you, that my student contacted you, and I'm here giving a keynote. I'm an aerodynamicist. I'm no computer scientist, but we need to work together. So here's the vision of the roadmap of NASA. So it's quite big. I won't go, I will just keep. We want to do the physical modeling as I've described you. You want to work on algorithm and the geometry and the multidisciplinary optimization. But I find it amazing that their first and parallel stream that goes in all these is high performance computing. So they're aiming at 30 exaflops by 2030. And so you can see that without high performance computing, we cannot achieve the physics modeling, the algorithm, and what we need to do in aerospace. So HPC is key. And so how do we embody this vision? We embody through the American Institute of Aeronautics, which is the institute that brings together aerospace, aeronautics together. And we do workshops, just like this workshop, this Chappelle workshop. We do a workshop for better aeroacoustic, better supersonic flow, better drag, better geometry, and whatnot. And who participates? Well, the industries, Boeing, Lockheed, I missed the K here, sorry, Brad, GE, Textron, and Bombardier of this world. So it's international, Dassault. We have research centers. You have NASA, but honor are quite good too, NRC and JAXA and DLR. And we have universities, Stanford, Oxford, Norway in wind simulation, and Canada. I just list myself there. And we have certification agencies that work together to certify aircraft. So all these meet in these workshops. And when we meet, we look at CFD. And so we get national we get National Research Center CFD. So your NASA in the US is making software. And the NASA of France, UNRWA, is making software, but they're tagged with export control. Industries are making software. So Boeing, Bombardier, Dassault, Airbus, but they're tagged proprietary. So this is where universities come to play. We're using open source, we're research-based. So Stanford, Michigan, Toronto, and Polytechnique Montreal. So we can use our codes that are almost as good as the other codes. Now, it happens that the university codes are certified. The university codes are not certified by the authorities, but basically we reproduce in our lab so close that we can start taking chances, we can start putting Chappelle, do stuff like this, and then it cascades up. So some history, you can see that high performance computing from the convex all the way to today's 15,000 core machine at Bombardier they have now, goes along with code development and goes along with the physics. So the first transonic problems were done on a wing, even a 2D wing, 3D wing, and now we can do viscous flow with separation, and now we can do full aircraft. And this comes by means also in progress, in paradigm shift. And so what was amazing is that Brad and I met. So the students that Brad described are responsible for some of my gray hair. You don't see them, but they're there. And some of my stress. And I lived that, funnily enough, exactly the same thing as I was at Bombardier with a Fortran code, and I was in charge of making this code treat more geometries. And so they forced me to use a language. And so this is a real story. At night, my colleague and I, for 4 months, we programmed a parallel code in C, never told our staff. at Bombardier. And then when the time came to show the solution, we showed the solution, they congratulated us, but we told them that it was in C, not in Fortran. I closed my eyes, either I was fired or I was promoted. So that day, they congratulated me and they said, okay, you're now the head of the R&D group. I guess they couldn't fire me. That's why they didn't fire me. They couldn't. So that was a technology shift at Bombardier. And now my student did the same. They asked me permission to write in CHIUW the code. I said no, just like my supervisor said, but they said, well, it's already done. And so they put me right in front of the fact, and I thank them for that, because that's how life works. You know, history repeats itself, and a technology push comes from the students and those who are in a place where they can take more risks. And we need these people. And so I thank my students, and I did not challenge them and I did not fire them because I needed them. So we have made the move now to CHIUW. And so in this history, you can see that they go tight, hand in hand. So we went from 1970 to 500 degree freedom to now more than, you know, 1 billion, 300 million here, but we're now at 1 billion, and it goes hand in hand. So to show you what CHIUW did in our lab, I started my lab. So after my 15 years at Bombardier, I became a professor in 2011, 2012. So I wrote NS code myself, gave it to my lab, and we added physics and all this, and it ended up 120,000 lines. And my student said, we can't handle it anymore. It's too complex. We lost track of everything. And today, they went from 120,000 lines to 48,000 lines, so 3 times less. But the code is not 2D, it's 3D. And it's not structured, it's unstructured, which is way more complex. And it's multi-physics, aeroelastic, aeroicing. So I've got industrial type code in 48,000 lines. So for me, this is like the proof of the benefit of CHIUW, plus the smiles I have on my students every day at the lab, because they love CHIUW as well. So that's key, that's the takeaway. And so CHAMPS, so that's the new solver that has been made, and all made by the students. And I did not program one line, I'm happy to say. I can't, and the students do a better job than I do. So it promotes the programming efficiency. It was easy for them to learn. So they tell me, but I see the end result. We ask students at the master's degree to do stuff that would take 2 years, and they do it in 3 months. And I'm not joking. This is like from 2 years to 3 months. So if you want to take a summer internship and you say, and I've done that in my lab, program a new turbulence model, well, they managed. And before, it was impossible to do. So it's much easier. So it was initially developed by 3 students. I heard it was in their basement. Just like me, it was in the attic where I am right now. I'm in the attic. And we're now looking to make it compatible with GPU. So there's going to be a presentation by Anthony Bouchard at 2:15. The icing part will be done by Hélène later on today as well. And so we can now do aerodynamics, we can do icing, aeroelasticity, and mesh generation. And in order to prove that CHAMPS is world-class, and it's a code that I've been sharing with Georgia Tech, and that I'm happy to share with anybody that needs a code to test a few things. We believe it's a world-class code, so we participate in the AIA workshop that is coming in July and the Heidelberg workshop in August, and we'll show our results, and it's going to be compared to Boeing, to NASA, and we're up there. Just like Brad showed that CHIUW was up there with MPI, we have benchmarks, and we show that we're up there. So I'm very happy that we've achieved this, and I thank Brad for letting us run on the supercomputer there. So just a few examples like this. When you have icing, you have novel, they're called lobster tails. So anybody that ate a lobster, or in Maine, we call it giddy, but lobster roll, I guess it's lobster with mayonnaise. So this is new physics. And now we have a model that has been done here in Canada that can highlight this morphogenetic thing. Nobody had managed that ever. So NRC here in Canada managed that. And that allows, and we've now come up with our own way of doing it. And you can see the result of CHAMPS today. So we're building up this layer, let's say on a 20-minute ice shape. And the last ice shape result is spot on with the experimental data that is in pink. So I congratulate Simon and Helen for doing this prediction. And now we've moved up to stochastic model. So a stochastic, you need a random number generator, and then you can have, if you repeat the experiment, you don't have the same result, which is what we see in the experiment. You can repeat experiment, you can repeat flight testing, and you don't see the same amount of degradation. So with this method, you can repeat the degradation that is stochastic. And it's more than porting a code from C to CHPL. Helen tells me that you need to think about memory management, about the parallelism, and adding additional types such as heap and list. So it goes down deep in the code. So you can see our presentation at 11:15. We do aeroelastic simulation. So you can watch this video. It's kind of funny, but also scary. But this is wind tunnel. Back in the old days, you can see it's old, but nevertheless, the data from those tests are still used today. So we have to make sure that the airplane withstand aeroelastic instabilities. And so it's not easy to do scaling because you need the right Reynolds number, the right mass matrix. And so this non-dimensional analysis is not easy to obtain a dynamically viable scaling. So what is aeroelasticity? Is you have aerodynamics, you have inertia, and inertia is a bumblebee that arrives in front of your shield and just hits your shield because it cannot navigate the car radius of curvature. So it's gonna, the inertia of the bumblebee would just hit the windshield, and you have elastic forces. If you have antennas on your car that used to, on old cars, the antennas used to go, and then you can have aeroelasticity. And so basically, we are starting to integrate now, and this is key in CHPL and in high performance computing, is you have aerodynamicists like my group that develop a CFD software in aerodynamics, and now you have to link this code with another group that has done elasticity with Nastra. That's the most famous code. So how do you hook up two codes now? So we are looking at the computational science challenges in merging an external code with an internal code and how they can communicate together. So that's what we do. And here's an example of results in the drag prediction workshop that was held a few years ago, but now we've had a chance. So each line is several codes from NASA, the NASA France of Germany, all the industry code and university codes, they're all there. And as you refine the mesh going leftward, so as you go from 600,000 mesh points to 100 million mesh points, you're supposed to arrive at mesh independent results. So CHAMP is the blue line here, and you can see that we're in the middle of them, and we have low sensitivity to the mesh, which is a good metric, and so we're up there. We've also validated on a complex configuration with the NASA code, and we have the same slope, more or less, and so we're benchmarked with NASA. I give you an example of skin friction line. You can see how complex it is, the flow that comes from a slat over a main element and over a flap on takeoff. You even have some strange devices on 737s, like these vortex generator that generate vortices that help stabilize the flow. And when you look at the experimental visualization. So we actually put oil flow, and now for recycling, we use olive oil, real olive oil. So in California, to do those flow visualization, and you can see patterns where the flow separates, and this is the numerical simulation. So you can see that right now our physics turbulence model picks up too much separation compared to the experiment. So we will have to work on the physical modeling. It's not easy. And you can see the complex flow on a engine that you may see across the window next time you take a plane, when things will happen. So you can see that you have corner flow separation, you have vortices flying off, and you have complex geometries, and you can see that the simulation is trying to replicate that. So in summary, hopefully tonight when you come back to home, you can say I've learned maybe something in aerodynamics. So we have 3 phases. We have a conceptual phase where businessman will come and see you, say, Brad, would you like to buy a supersonic jet? And you would say below 100 million would be fine. And then once they do their work, they do preliminary design, and they go and see you and they say, well, maybe it's not 100 million, it's 120, is it okay? And you say yes, and then you go to a detail phase. Aerodynamic analysis needs that the community of physics, applied mathematician, and high performance computing get together in order to solve the aerodynamic problem. It involves a complex workflow, parameterization, the CAD, the mesh, the solver, the post-treatment. So that's one problem was that the CAD, CATIA works on Windows, but the supercomputers for the solver works on Linux. That was a real problem that was solved in an industrial environment. And so we rely on accuracy and computational resource, so it needs to go fast, and we need memory. So when we're now going to GPU, memory bandwidth becomes an issue. And so I'm saying that money is involved between each phase, and we're solving of the order of a billion unknowns now. So the high performance computing advances that you are making as a community have had an amazing impact on aerospace industry. I remember in the year 2000, I said to my staff and to my vice president, we're gonna solve Navier-Stokes. They all laughed. And I was using a supercomputer that I was sharing with the weather prediction in Canada. And everybody laughed, but the day that I solved it, and when I say I, was actually the community. The community solved it, and me, I solved it at Bombardier. Then they just wanted more and more and more. And so now aerodynamic was the first in supercomputing at Bombardier. Structural came second. Electromagnetic, flight simulation are all fields now that are using supercomputers. The hardware has had a tremendous impact, and we're looking to go to GPU. And I've heard this morning that GPU is a nightmare because you have students, they need to learn the algorithms, they need to work MPI, CPU, and then you add GPU, it's another layer. And right now it's quite difficult to do that. The software, you know, we went from strongly typed Fortran to abstract language. And some, like in France, they went overboard with C++. Their code was not efficient enough. And now Chappelle seems to have struck the right balance. And I will help you convince other people if need be that Chappelle. So I'm in sabbatical this year. So hopefully I can take time to show Chappelle impact to the French agency and to NASA. I should be able to do all that. Multidisciplinary knowledge is key for future advances, enacted through multidisciplinary collaborative efforts from the modelers, from the mathematician community. So I welcome, I've already had discussions with some of your community, and I'm very happy that you engage in it, and I see that you need it as well, so I'm happy. And these challenges are all captured in NASA's vision. And NASA has the buy-in. By the way, the NASA 2030 report was disseminated in a beta version to get the buy-in. And I was one of the people who revised the NASA vision to get the buy-in on my side. Bombardier was on it, and Airbus and everybody was on it to make sure that the international community has a buy-in. And now we have NASA's vision, and everybody is aligned to achieve those objectives. So I end this talk. It's 11:45. So I just thank again the organizing committee for such an appreciated invitation. And I can't believe it's my first keynote, by the way. So I thank you and I thank the community, because my students tell me this community is active. They send an email, they get an answer, and that is key. So we thank you. And I wish you a safe and happy and planet-friendly flying when we'll have the chance to do more and more flying post-COVID. Thank you very much.
Eric, thank you very much. I think that was a great talk. It was very entertaining and very informative for those of us who really don't know your field nearly as well. Very approachable. And more than anything, I think to me, it was really motivational in the sense of, sort of pointing out the need to kind of always strive forward, whether it's in sort of new numerical methods and techniques or HPC generally or new programming models. So thanks for bringing us that message today.
Yes,
if you have questions for Eric, I've just posted the link again to the Slido in the chat. Please post them there. And I'm going to start out, Eric, with a question from Michelle that I think would be useful context for those of us who really don't know how the aeronautics field works very well. She asks, can you speak more to the relationship between industry and academia when designing planes in terms of who is doing what research and what development and the funding? Kind of like, how do academia and industry work together and who owns what, if that makes sense?
Okay. Yes. Very good question. Follow the money and you'll understand how things happen. So it's very important and it's key. So what happened is universities are there. This is no question for sure. Universities are driving the technology push in terms of novel capabilities. So you may have heard of the adjoint method that has been developed by Anthony Jameson in the 1970s. And so the universities are developing novel methods. And these are funded with National Science Foundation, NSF, or NSERC in Canada, with fundamental research funds in which the industries are not even involved. And as soon as these technologies, these novel scientific advances are making their inroads into the scientific community and applicability, then the industries take it. And then they'll say, well, we're going to fund joint industry university efforts. And so in those joint efforts, we take the technology from university and we bring it on prototyping scenarios in industry. And once it's in there, they take it alone, and with their own money, they will further develop a real code that is certified, and they will go through all the certification phase with the authorities. So that's how it goes. NASA, by the way, NASA Aerospace is leading many of the industrial community because it's a heavy industry. When you think about SpaceX, Airbus, Boeing, these are companies that develop product of timelines of 100 years. We're not talking iPhones of a lifespan of 3-4 years. If you design a commercial aircraft, it takes 20 years of R&D. It takes 15 years of development. It's 45 years of in-service, and it's 25-year recycling. We're talking 100 years, not 3 years. And so because it's a heavy industry, it relies heavily on safety. It's low risk. So the risks are taken by my research group, by the community and universities. And slowly, the NASA has defined technology readiness level scales that goes from 1 fundamental to a potential application, 3 application proven, 4 application in a laboratory environment, 5, 6 in the university, in the industry environment, And this scale allows to even have worldwide financing level in industry that tier level 1 and 3 goes to academia, 3 and 6 to industry and academia, and above 6, if you have funding from government, it needs to be in the general agreement and trade tariff agreement. So it's quite complex, and you need to do this in order to be a good at attracting funding.
Great, thanks very much. I'll just add something that's been interesting to me that I think others in the audience might be intrigued by as well is some of these workshops that you and your team participate in are, to me, like what workshops ought to be. And I guess ours is sort of a counterexample in the sense that you are tackling a common, large, significant
Yes.
problem jointly or sort of independently with other groups, and then sort of getting together to share results and compare results. And I assume that that's another important part of transferring some of these techniques and knowledge from, say, academia to industry. Is that accurate?
Yes. Yeah, this is accurate. So there's something that is kind of unknown that I like to make a point here. Boeing and Airbus are working together when it's term of security, and Boeing and Embraer, they are together. CO2, global warming, are tackled together with Boeing and Airbus. I had the chance, let's say humbly, one of my best experience, I was member of the COP16 Conference of Paris Global Warming Conference in Mexico. Unfortunately, nothing was signed in Mexico. It was signed in Paris. It was signed in Montreal for the fluorocarbons. Nothing was signed in the one I participated, but the goals remained the same. And so I was with Airbus and Boeing defining the aerodynamic target for CO2 emissions. And so we worked together because a Boeing aircraft that crashes, COVID, is not good for Boeing, Airbus, Bombardier. So they're working together. And so those workshops are purely scientific, and the science, let's say at the noble effort of sharing scientific exchanges with competitors. And we do that. And we come up and try to understand what is, how to make things better. And we do it.
Great, thanks very much. So let me go to a question from Rich Vudik. First of all, he says, great talk. He asks, you said that industry was not using models like URANS, DES, LES, and DNS. Do they not need that detail, or is computational cost the limit there?
Yeah, the computational cost. So first of all, I think going back to Michel's question, they all have their own proprietary software. So even if NASA develops it, Boeing will wrap it, will modify a parameter here and there, will make their own sauce, Bolognese sauce, and will certify it. So it's proprietary. And they have access to LES, DS, so higher turbulence model. They might use it on an accident. They might use it spontaneously on one thing here and there. But what stops it is that 80% of the development costs are made in preliminary and conceptual design phase. Those early phase where you iterate with so they're made in the quick turnaround. Are you 100 million? Yeah, 120 million. And when you make those decisions, you don't have the time. And so you use steady flow equations, not unsteady flow equations. And so they're aiming to have DES and LES in 2030 is going to be an unlimited case. But believe me, when they're going to do the aircraft design, they won't use these because you need hundreds of millions of CFD runs to hone in the design, because you're testing the crashing cases, the limiting envelope crash cases. You're doing the aeroelasticity, aero-icing, electromagnetics. You interact all this together. You need fast turnaround codes. So you need a breadth, high fidelity if there's an accident, maybe, but more often than not, you need fast is key.
Great, thanks very much. A question from Mike Merrill. Can you say anything about breaking down the barriers to multidisciplinary teams?
Yes. First of all, this is a great question. They're all great, by the way. In companies, and you work in companies. Now I'm in, but in companies, you work in different departments. They call it friendly competition. I mean, they're not so friendly. And so I remember in aerodynamics, we used a time domain, and in aeroelasticity, they use frequency domain. And we used to laugh to each other. And nothing is better than communication, understanding each other. So some do multidisciplinary training. So you take a person, you put him in another department, and you do vice versa, and suddenly understand that they're not stupid, and it's because there's a reason. And so if you start to understand each other, and if you start to understand the details, not just the overall, but the details. So if you have people that have been doing multidisciplinary, so they have been in aerodynamics, they have been in structure, or they've been in computer science, then you get the buy-in, and that breaks the barriers. It's a little bit like, I guess, with humanity. You know, I did my master's and PhD in other countries, and you get to know the culture and you learn a lot. So I would say communication is key, and working together then, you know, not just communicate, but then working together. That would be my suggestion.
Great, thank you very much. Let's go to a couple of kind of concrete questions. One is, do you run Chapel on Compute Canada clusters? And if so, which cluster?
So we run CHAMPS, our solver, and all other solvers on Compute Quebec. So we have many clusters. It's called Beluga, where we're running it. So you can Google it. Beluga is a dolphin in the Gulf of St. Lawrence that is white and that has a long nose. And so it's not a whale, apparently. It's some fish. I forget there. I'm sorry, what is a beluga? But it's a white type of whale that is not a whale, I believe. And so we're running on beluga, but we're running also on the on Craze system. Sometimes we run, we debug because InfiniBand on beluga is slow, and sometimes we can solve issues on running on HPE clusters. And if maybe another student of mine, Simon, may want to jump in to answer the question, or Mathieu.
Yeah, actually, no, you answered correctly.
Good.
We use Beluga, and I had already answered in the replies.
Good. Thank you.
Let's go to the next question. This is from an anonymous asker. What does it take? You talked about certifying codes earlier. What does it take for a code to be certified? Okay, so a very precise case is icing. So you wanna demonstrate that the aircraft we're flying in is safe when it encounters icing. So that means that you need pilots that will fly and show that it's going to be safe. But maybe there are regions of flights that it may be too dangerous to have a human being in the plane in the first phase. And so we are starting to look at, well, maybe in so certification typically is 1 of a billion scenarios. And maybe you find that there are some cases that are more than 1 in a billion, so you want to test, but they may be impossible to fly in. You know, if you have 2 in a billion, you can't certify. That means you need to put pilots to fly in a 2 in a billion test case, but they need a lot of flying hours to get those 2 cases. So maybe you need to simulate those. So this is where it comes, that you want to simulate, you want 100% security for the people, but maybe it's not easy to have flight testing. So you do simulation testing. So what does it need? It needs that FAA, which is like your Food and Drug Administration, FAA, Federal Airworthiness Authority. They check your process, and you validate your process, and you extrapolate your process, and you show that it's robust, that it's safe, that if there's a modeling error, you're on the safe side. If not, you have a security factor. And all these wise men at FAA have a job for life. They can criticize anybody because they're like a professor that have tenure. You have people at the FAA
They can go at Boeing in any meeting. They're called DADs, Directory Aerodynamic Directors. They can go in any meeting at any time in any company and listen and report on it. So what happens in the aerospace community, we may end up with this. It's a self-certifying industry. And we know Facebook and all this, these are difficult questions, but right now, the safest industry on earth is aerospace. Despite the few crashes you see, if you look at the number of billion flight hours we have, we are the safest industry and it's working quite well. So there are processes that we go through, just like the COVID vaccines, in which we certify numerical codes.
Great, thanks. And as you noted, we're just about out of time. I want to thank everyone who posted questions. We didn't quite get them through them all, but I'm going to throw one more at you just because I think it's probably on people's mind. Is your CHAMPS code open source? And if not, are you planning to open it up where that could be, as we've talked about before, giving it away, but not developing it openly? Or it could be full out developing the whole thing openly as well.
Okay, so we have in the community, in aerospace community, some research codes, they're called. So we exchange it between researchers, and because NASA is a research enterprise, it's not a commercial enterprise. So when I work with my companies, I've got full IP with researchers. So if researchers want to use CHAMPS, I don't even have to ask permissions to anybody. We just do it. Now, if it be open source, I mean, we're that close of doing it. So we're really thinking, so please engage. We're open to it. But right now I gave the code to Cray, HPE. I gave the code to Georgia Tech. I gave the code to Onura. And so if anybody wants the code in order to do research, it's no problem.
Great, thanks very much. And why don't we end there? Éric, thanks again very much for the talk today and for taking the time to answer our questions. We really appreciate you having you here at the workshop this year. And we're looking forward to hearing more from your students later on this afternoon.
Good. I'll stay during the break if there's any more questions or in the chat.
That sounds great.
Thank you.
And